know. So just now we mentioned the random errors. So look at random error here. We actually have three types. The first one just exactly the measurement error, 测量误差. And here it just means the observed value differ from the true. Yeah, for example, if you have a regression like y equals x beta plus epsilon, right? And then you have a fitted like y hat, then your observed minus the fitted the true one. Yeah, like here these two would be some measurement error. And next one is about the recall bias. For this recall bias, that means participants fail to remember past events accurately. And then for response bias, that means give inaccurate or misleading answers. Yeah. So response bias seems like may include the recall bias. And here, what's the reason then? Like for measurement error, is the instrument's imprecision, or just like the environmental noise or human error. So this is a measurement error. The second one, like the recall bias, this is the human memory limitations or selective core, right? But for response bias, this one just means the participants desire to please interviewers or avoid sensitive disclosure. Yeah. And then for three of them, it would have some bad effects like add variability, reduce the power, or just like the data inconsistency or misclassification. And even sometimes it will disorder the survey results. Yeah, this is one that we have. Next one, among systematic errors, sampling bias is particularly important in empirical study. And here we particularly want to compare with something we call it the confounding. You know, for confounding, this is really important in causal inference. Yeah. So what do we understand this? First, let's see the concepts. For the concepts of confounding, this one just means it's a systematic error, but arise from uncontrolled relationship between variables rather than from the sampling process itself. Yeah, so confounder, for example, the environmental confoundings. So here we have table 6 compares these two sources of bias, highlighting their differences in definition, origin, and impact. And here we can see for confounding and sampling bias, if we see the definition, yeah, this is always the most important part. For confounding, that means an external variable, and then it affects both the treatment and the outcome. I mean, for both sides, it would affect. It lead to the biased. Yeah, here you see the bias estimation, the causal effects. So confoundings, yeah, or confounder, yeah, people would like to pick out. But for sampling bias here, it means that here you would impose improper sample selection. So this one would cause the sample to be unrepresentative of the population. Sampling bias, yeah, the bias from the sampling, right? So this one would lead into a systematic deviation from the truth. Yeah. So this is the definition. And also let's see the impacts. For the bad impacts, you can see confounding would distort causal inference, possibly creating spurious positive or negative association. Yeah, this is one thing. But for sampling bias, yeah, this is systematically overestimates or underestimates the population parameter. Yeah, that means it may be skewed to the left or right hand sides. And then for the stage of occurrence, yeah, here often occurs during the analysis stage if control methods are not implemented. However, for sampling bias, primarily occurs during the data collection. Yeah. So for these two, if you want to prevent, so you have to start at a different timing. And the common solutions like this one, you consider random sampling or broaden the sample coverage. And for the confounding, you try to do the randomization or just use the matching or stratification or even like regression adjustments. So next one, we would want to show you some causal inference and particularly the looping causal model. Looping, yeah, yeah. So this is a statistician. He stayed in Harvard for many years, and several years ago he transferred to Tsinghua University. Yeah. So this person has many achievements in statistics. Like the causal inference is one of his fields. He has another field like the statistical missing data. When I was a PhD student, I read his book with Professor Little. So they have a book like statistical inference for, statistical analysis for missing data. Yeah. And then I learned MCR, missing as random or missing completely as random, long ignorable missing list, and etc. And like my graduated PhD last year, he also studied Lubin's work, like Gelman and Lubin just gave some discrimination rule on MC sampling. And then my PhD just present some method that can not only discriminate, but also like we can make sure the MC convergence. Yeah. So this is just a story related to the Rubin causal data. But here we have to check carefully about observational data and the confounding variable. Yeah. So for causal inference here, that means you have observational study and then you try to fix more things. Confounding variables, sometimes we call it confounder, can bias the estimation of causal effects. So this is really bad. So then the goal of attention here, causal inference was popular 2 years ago because 3 people got Nobel Prize on it, right? And then a lot of people turn to it. So here, the goal of causal inference is to identify the causal effect of a treatment on an outcome, isolating it from spurious association due to confounders. Yeah, this is the one you guys have to keep in your mind. Yeah, you see in this course, principles of data science, we have to deliver many concepts from probability, statistic, machine learning, transfer learning, knowledge model. Yeah. Okay, next page. Yeah, you can see here. Here is a general framework I hope you guys can grasp. Number one, under the looping causal model, each unit has two potential outcomes like Y1 or Y0. Y1 outcome treated just means if treated, it would be 1. Untreated, it would be 0. So the individual causal effect would be what? Would be their difference. We denoted by tau. So here we can see usually like only one of them is observed. We call it a counterfactual problem. Counterfactual problem. So here causal inference focuses on population level effects that can be estimated from the observed data. And then here we need to introduce a concept, average treatment effects, ATE. So for average treatment effects, that means what? Average just means you take the average treatment effects, like you use Y1 minus Y1, Y0. Next one, like the randomized assignment ensures this one. So this one just tells you, one try to eliminate the confounding so that, yeah, here your HE would be what? Would be just doing this way. And then you can further estimate it by what? You can see This one, use a bar to means the sample mean, right? So here we use the sample mean difference to estimate or approximate the true average uh, treatment effect. And here you can see, here we show several typical scenarios. Binary treatment like 0 and 1, multi-value treatment or continuous treatment. So here for the aspects we can track, for each of them, like here you would have some outcome, right? And then for individual effects, for these individual effects, we just do in this way. For average treatment effects, yeah, so this is one that we have. And for the different scenarios like drug against the placebo or different drug dosage. Yeah, for this one, I can give more example. Yeah, you see, like in medical image study, if you go to see a doctor, medical image would be a very highly frequent test used a biomarker. Yeah, for such medical image biomarker, like if people want to scan you, right? Sometimes they would ask you to take some dose. But such kind of dose may be harmful to your body, particularly for those people who might be pregnant, get some chronism disease, or very junior, like a child or senior people. Yeah, in that way, you have to reduce the dose. But meanwhile, you want to see more clearly, I mean, or just say you want to observe the image and obtain more information, right? So you have to control the dose usage. Here, like if you use the normal dose, fine, or 1/4, 5/4, or even 0, and then you just check what would be possibly observed from the synthesized image. Yeah, 合成图片. Yeah. So in that one, then it has some specific study. So here the different drugs dosages would take the therapy into several different categories. Okay. How do we measure statistics? Here, I think this one we discussed at the very beginning. For example, like the central tendency, variability, dispersion, or just like the position and the shape. For the first two, you guys are familiar very much. The next one, measure position. This one just tell you indicates the relative standing of value within the data sets, like the percentiles, the quartiles, or the score. So that means words you want to check over some distribution curve. You want to see like a box bars is the first quartile, the third quartile, or just the medium place. Yeah. So this is something we discussed many times. And also here you can see we actually have something that we mentioned like a mean, median, and mode. For each of them, besides the purpose here, for the definition I mentioned already, for the purpose I mentioned also, here we can see the pros and the cons. What's the pros? Pros means advantages, cons means the disadvantages. Like for mean, easy to calculate, but highly sensitive to outliers, right? And then for median, lots affected by outliers, but usually does not use more information. So in computing is hard. The third one for the mode, that means for raw numerical data you can count, but may not be unique, and also it is unstable for continuous data. Yeah. For the next one, like the measurements about the variability and the dispersion. So here is some knowledge you guys need to grasp. The first one is about range. Range just use the difference between the smallest and the largest. So this is a rough measure spread, right? So for this one, it's simple and intuitive. Yeah, but attention is highly sensitive to outliers. The next one, like the variance, variance is solid theoretical basis, but not directly interpretable, right? The third one is about the standard deviation, or just like standard error. So this one, I think no much difference between these two. Yeah. And next one, like the CV, coefficient of variation. This one compare variability across different units of means. So it is unstable when the mean value is 0. Yeah. But it provides some cross dataset comparison. Yeah, this is one. Next one about the position measurements. For position measurements, like here, for wall of 3, require sorting, like percentile. Sorting means what? Sorting just means you rearrange it through some ascending or descending order. And for quartile, not much difference, only 100% difference. A coefficients, right? Constant coefficients. For Z-score, this one requires mean and standard deviation. If run normal, there would be some trouble. You need to do some calibration. Next one is about the measure of shapes. And here, skewness and kurtosis, I introduced this already. Yeah, I do not mention much about that. But next one, you guys should to keep in mind. Here, the first one is about the L1 loss. If you have L1 loss, then you would say there would be L2 loss. Besides L2 loss, you may have some L infinity loss. But I think at least you need to grasp L1 loss and L2 loss. For L1 loss, here you can see this minimization. Usually you use the words list, right? Minimization means list. List what? Here, like this one, absolute value, right? Absolute value. Yeah. So, and then next one, like the difference here. So this one would be what? Would be the deviation. Yeah. So sometimes you would see LAD. Yeah. So LAD means what you would obtain some L1 loss. But then for L2 loss, so what does L2 loss mean? L2 loss just means here you still try to do something like minimize and still summation, but here you use brace of square, right? So this one is a L2 loss. Sometimes people would say this is a square loss, right? This is the square loss. Yeah. Yeah, so this is the 2. And here for the result here, median as the minimizer of one loss. Yeah, so that's why some people use median as a measurement. But also remember, if you deal with median, mathematically it is harder, more complicated. But if you use the mean value, so last one is much easier. So L1 loss, L2 loss. Here, yeah. Yeah, people may also use like a K-median clustering. Yeah, this is something like the mean absolute error, MAE. Yeah. The next one, like mean plus SD, and is relation to the Z-score. So here we have the single variable case or relation to the Z-score things. Yeah, this is the one that we have. Next one, I want to introduce the multivariate extension. This one is very useful, particularly, in the first lecture, I mentioned the Gaussian distribution. For Gaussian distribution, when you have a Gaussian distribution, we say, yeah, we say like here I use a x, right? So in this one, we'll try to write it. Yeah, there would be some square root n to n, and here would be some star. You have to check what it is. And then here add some exponential parts. And then inside, it includes something we say constant. Yeah, here I just write the format. For the detail, you have to check what it is. Yeah, so here I just want to tell you here for DMX is very useful. And for this one, for this multivariate extension, it has a name, Mahalalobas distance. What does it mean? It's actually, you may do it this way. Yeah, you see, like for the one here, I mean, yeah, for this one, nowadays people use sigma minus half and sigma minus half. Yeah, people would like to use it in this way. That means what? That means you actually can do more things. For example, you like, yeah, you see, if I bracket the first part, it means what? It means that for the second bracket for this one, it equals to what? Some transpose. And then inside it would be like x, yeah, and then minus mu and the sigma half, right? Yeah, you see, you actually can write in this way. Yeah. So this one just like a square, yeah, square something, yeah. Okay, so this is our multivariate extension. Okay, and also like multivariate standard deviation, when it is in some ellipse, 就是一个椭圆形. So here in such a situation, usually it is safe to say it would be a Gaussian distribution. Yeah. So this is something we want to introduce. And here comes the correlation coefficients. Yeah, this one also some concepts that you guys need to grasp. The first one we want to introduce is the most common one, the Pearson correlation coefficient. Yeah, for this one, I suppose everyone knows how to do that. But here I want to draw your attention again. When we see this one, we care about the direction strength around some linear. This is a linear association. See that? Not some non-linear thing. So this is a Pearson correlation. And here we just know like a positive, negative association or no linear association. Yeah, for Pearson correlation, you know that. But besides this very common one, we have several other choices you guys should keep in mind. Like Pearson, and the next one is about what? Like the Spearman's rule, candles tau, and point biserial R. This one seems very easy. For point biserial RPB, it's the measure relationship between binary. Binary means discrete, and then continuous variable, right? So that means this one is very special. You know, if the continuous and the discrete mixed together, usually mathematically it's harder. So this one provides you some measurements, like, yeah, here you can use these two to do product. Yeah, and this one works. So this is the point biserial. And next one, the candles tau here. Here it measures association concordant and the discordant pairs. So here tau is what? Here tau would be the difference with a divisor. For this divisor, it seems like n take 2. So here CD are concordant or discordant counts. For this candles tau, is very robust to outliers, because candles tau seems like use some information from the quantile distribution. So we know, yeah, robust but computationally expensive. Yeah, because you consider the quantile. Next one, like the Spearman's rule. This one just measures the monotonic relationship using ranked data. And here comes out a formula. And here DI is the rank difference. So this one works for ordinal data and is robust to some nonlinear monotonic relationships. And here you can see it's not as good as Pearson. Pearson correlation, if you consider a linear relationship, but if it's a nonlinear relationship, so Spearman's rule would work better. So here for these four, you have to understand for like each of them, say how to calculate them and in what situation you recommend whom. Okay. Here, for these two things, we have two remarks. The first one, linear and non-linear. Here, people care different. Right now, as we have many NN, the deep learning, the deep NN, right, neural network. Yeah, we have various deep NN. So for nonlinear, we can do. For example, you can use CNN, RNN, even vision transformer to model some linear relationship. The second one, attention, when we try to have a correlation coefficient, for example, today we summarize 4, but it does not mean that you can explain something like the causal inference. Yeah, so this one tells you even a strong correlation does not imply the changes in one variable cause changes in another. So here, to establish causality, it requires a controlled experiment or other rigorous statistical methods. Yeah, be careful about this point. Okay, so next one, finally, we introduce the empirical rule and the inequalities. For the empirical rule, attention here, for the data that's approximately bell-shaped. You know, when we mention bell shape, it is symmetric. Yeah, for normal distribution, it is bell-shaped. Empirical rule states the following proportions observations lie within k standard deviation from the mean value. So here you have 1 sigma, 2 sigma, 3 sigma, and then each of them means words. Here you can see it means some events occurs and it may fall, yeah, it may fall into a special area. And such area tells the possibility it occurs. So that's why when we mention 3 sigma methods, it's like you are more strict than 2 sigma. And if you mention 6 sigma, seems like your standard becomes extremely high. Yeah. And next one, we want to introduce the some inequalities. Here, yeah, it's quite mathematical, but don't worry, I would not test it. But you guys need to know this is a very important technique. Yeah, you see, many times you have to calculate the upper bounds, lower bounds. So when you try to have a upper bound, lower bounds, then you have to use some inequality technique. Yeah, here we tell the first for Markov theorem. This one tells you if you consider the probability y survive time t, then this one would be bounded by what? The quotients between e of y against the t. Yeah, this is one that we have. Okay, so this is the first one. The second one, the generalized Chebyshev inequality. So for this one, here we can see if you consider absolute value that is greater than t. So this is a two-sided probability, right? So in such a situation, you can further give a transformation. For this transformation, attention, this transformation is wrong decreasing. Wrong decreasing. So when you apply it, you further have what? You further have 5 here and 5 here. So that means compared to the above, look at the upper place. Here we still have some average of the y or phi, but it's still the quotient against the t or just the phi of t. Yeah, so here you may compare these two, the Markov property or just like Chebyshev inequality. So okay, for this part, I think by far I almost finished. Yeah, so this is one. Now I go to a new part. Yeah, confidence interval. Yeah, for this one here, actually like in other class, I do not mention much. I just like to go to this place. Yeah, go to this place and go to the first page. Let's go to this place. Okay, confidence interval estimation. Seems like today when I ask our classmates, many people answer to me, you guys major in statistics. Yeah, maybe, but I remember if I look into the class composition, lost like only from one. Maybe I check later. I remember for our evening class students, you are medical data science, right? Yeah, you belong to medical data science. Yeah. So here for confidence interval, this is very important, but you guys may know that. If you really do not know that, yeah, you check the this document's name is supplementary. And for this one, it contains 69 pages. Yeah. Yeah, go to this place. Yeah, if you forget or if you do not major in uh, like statistic. So you go to this place. Otherwise, I will jump to my slides there. But before we go, let's go to this place. Here quickly, let's go through why isn't a point estimator enough? So that means why do we introduce the confidence interval? The reason actually tells you what. If you use the point estimator, it shows the fundamental weakness. They do not provide the precision of the estimator. So confidence interval can provide the precision of estimator because you can see the width or the length of the interval. Last one narrower or smaller, that means more precise. So this is the first thing. And then next one, like random interval. So what does a random interval mean? We mention random interval. That means here at least one of the endpoints or limit points, two end, right? So this one is a random variable. So this is random interval. And for confidence interval, this one tells this is the usual way to quantify the amount of uncertainty in estimator that is constructs a confidence interval. And usually here, confidence interval are ranges of numbers that have a high probability of containing the unknown parameter as an interior point. So this one tells you for confidence interval, it satisfies some large number theory, 大数定理. Yeah, that means from long run, if something happens, that means over 10,000, there would be a high chance it will occur, right? Yeah, this is about a simple about confidence interval, random interval. And also like two-sided confidence interval or two-sided confidence interval. That means you count about the two tail distribution or just look at one side. Yeah. So here 1 minus alpha calls the confidence coefficient or level, right? And here T1, T2 just calls the end or limit of the confidence interval. Yeah. Okay, so this is the fundamental concepts, but my focus would be here. Yeah, here you can see for this one is totally 8 page. And here we summarize the knowledge into uh, 8 categories. For each of them, here we just show you some preparation and then you derive your confidence interval. After that, we show some detail how you derive your two ends. Yeah. So this slide is done by my graduated MPhil student, Lulu. Yeah, Lulu Zhang. Yeah, the girl right now serves in Huawei. Yeah, she's good at communicating with people, and then right now she's a salesperson in Huawei at Kuwait. Yeah. Okay, so let's check here. Here we have a random sample. You see, here we use a IID, and then for this lane we say here we have the random sample. For random sample, that means it would be identically independent distributed. And next one here, the sample mean, you know, for this one, it would be 1 over n summation xi, right? Yeah, and then for sample mean, what's the advantage? You can see the mean value, the central tendency is the same, but the variation is shrank by what? By a divisor, m. How do we have it? Here you may even do some simple calculation. For example, you calculate the expectation of x bar. Sorry, lonely for I think for this mean everybody knows how to do, right? I just show you the variance. So this one tells you what? Tells you it would be variance 1 over n summation xi. Then for this one, you know it would be 1 over n squared, and then you have n times variance of xi. So that's why finally, if you cancel n here, then you have the smaller variance, right? So that's why sample mean next. But remember, sometimes people may do not care about the sample mean. They just use the sum. Yeah, sometimes they just use sum of IID. And for sum of IID, I have 2 books that study the properties, yeah, from the Russian. Yeah, and then based on this one, now you have a standardization procedure. For this standardization procedure, so here we use the notation. For this notation, we call this one equal in distribution. So what does equal in distribution mean? That means for both of them, it will follow the same distribution. For example, in such a situation, the distribution would be n0, 1. Yeah, standard normal, right? Yeah, this is our tilde D, just means in distribution, they are identical. And next one, you can see x bar is a sufficient statistic of mu. So what is sufficient statistic then? For sufficient statistic, that means, yeah, just like if you deduct some observation, the remaining information would be unrelated. Yeah, this is a concept, but hardly to judge. And if you really want to judge whether a statistic is sufficient, you use a factorization theorem. Yeah, 因子分解定理. So that means if you draw the distribution, you can partition it into 2 parts. And one part only related to your data, then you say like a test statistic inside. Usually it should be a function, yeah, a function of your random sample. Yeah, so that part would be your sufficient statistic. Yeah, if you have interest, you can go to like Google to see factorization theorem. But here I do not pay much attention to it. Yeah, because in statistics, we care about sufficient, but in the big data and data science, people may not care much that. And then accordingly, you would have what? Yeah, you can check this place. Here for this blank parts, this is the probability 1 minus alpha, right? So for this probability, it tells what? It is the possibility that such, attention. Yeah, this is your, yeah, look at this one. This is your test statistic. And this one would be bounded by what? By here, yeah, z half alpha, you see? Yeah, then we can see in this place, here, yeah, between them, the area would be exactly 1 minus alpha. The probability that such a random variable bounded by a quantile value would be what's 1 minus alpha. And then attention here, we just mentioned that z half alpha is a upper half alpha quantile. Yeah, you see, what does this one mean? This one tells that if we just if we just look at this place, you see the right hand side. So this is a upper half alpha quantile. Yeah, that means words. Yeah, if we look at the area here, we just label that this is half alpha, right? So this is z half alpha. Yeah. And here we just show you mathematically, if you try to derive it, remember, if you want to build up a confidence interval, then you have to calculate two end. And for each end, it must include what? It must include some random variable. So how can we have it? So the right-hand side, we just show you that this is the way we calculate it, right? And then the two ends, yeah, it comes out. Here is one end and here is another end. Yeah, so this one tells that the probability 1 minus alpha such an event, yeah, you see, the probability such events would be 1 minus alpha. And these two, remember, they are the same. Yeah, so I hope this one can catch your attention. Yeah, you should know how to do that. And next one here for x bar and s square, we just show you what it is. And for this s square, here I want to draw your attention. Yeah, for this one, you actually, like, if you give a divisor, it can further into, I mean, yeah, like it will follow some chi-square distribution with n minus 1. But for chi-square distribution, you know, here I just want to tell, for a chi-square distribution with a degree of freedom, you can define it by what? Summation yi square. And here I run from 1 to m. And here for every yi follows like a standard normal. Yeah, you can have this. You see, chi-square distribution can be, and also attention, here for yi and yj, they are independent or uncorrelated. Yeah, yeah, so this is something we should keep in mind. Okay, next one, we go to the situation case 2. Attention, the first one I want to say more. In this situation, sigma naught is known, right? Sigma naught is known, so that's why in this situation, you can use what? Standardization. Yeah, because here, attention, you actually put what? Put sigma naught square here. Yeah, you put sigma naught square into this place, and then you can have a standard normal. Yeah, this is one that we have, case 1. Next one, we have the case 2. Sigma naught is unknown. In such a situation, can you do in this way? For example, like xi minus mu over sigma naught. Can we do in this way? The answer is what? No. The reason is what? The reason actually lies here. As I mentioned previously, sigma naught unknown. You cannot put an unknown parameter into a test statistic. Otherwise, it is lost a statistic, right? So now sigma naught unknown, you then have to replace it by some other thing. Here, by some derivation, I mean for this one, here x bar minus mu square sigma square n. Here you actually can do something. For example, I cannot remember clearly, but roughly in this way. Yeah, and also you guys can go to any traditional statistical inference book to refer. It's like x bar minus mu over sigma naught. And below just like s square and sigma naught square. Yeah, if you just try to write in this way, and also here, like you give something like n, I mean, just like n minus 1. Yeah, n minus 1. Yeah, you just have this one. Is this right? N minus 1 square. Yeah. If you have n minus 1, that means here you should, if you keep n, so there would be, if you do, oh yeah, I know. Here should be some square root n. Yeah, this one is in this way. So then accordingly, you have it. Yeah, you see? This is the way how people write it. See that? So this is a quotient. Yeah, for this quotient, we actually have two parts. One is about in this way. If you look at this way, you know what it is? Standard normal, right? Yeah, this is our standard normal. But then for the next one, yeah, the next one look inside. Yeah. The next one, if you look inside, so the inside one would be what? Would be some like chi-square distribution with degree of freedom n minus 1. So that means what? That means here you have a standard normal against the square root some chi-square distribution with df n minus 1. And then this one then follows some t distribution with degree freedom n minus 1. So this is the way how we get it. Yeah, if you have interest, you can refer to any textbook to see. Yeah, and why do we make it so complicated? The reason lies that your sigma naught is unknown, and then accordingly you can see like again, here x bar s square. This is a vector, right? This is a bivariate vector. So this one is a sufficient statistic of mu sigma naught square. Yeah, and then now attention for these parts. You know, here is a quantile value, right? For this quantile value, remember, T n minus 1 is a student T distribution with degree freedom n minus 1. And for this one, we would say this is a upper half alpha quantile distribution. The reason is what? The reason is that if you look at the area here, this area is exactly half alpha. Yeah, this is one that we have. So we have the probability like absolute value would be bounded by such a quantile value, and then the probability would be 1 minus alpha, right? And then again, if you check the right-hand side, I mean, yeah, look, yeah, for this place, yeah, this is exactly what? This is exactly the inside one, but we try to do some mathematical derivation so that finally you can write two ends. One is here and the other one is here. So inside you can see you have what? X bar. This one is the function of your random sample, and also like S square is another the function of the random sample. That means here for this two end, it has randomness. So then accordingly, you know, for the inside, you just replace by it, right? It equals 1 minus alpha. And then you can answer that 1 minus alpha confidence interval for mu would be exactly, attention, here we have two writing. One just like x bar plus minus. Yeah, this is one way. The other one like you write to the interval limits. Yeah, so this is where you have it. Yeah, so yeah, this is the situation. Sigma naught is unknown. And then you come to the next one. Sigma 1 square, sigma 2 square are known. In such a situation, attention, here you have two IID sample, right? But the next one is important. You assume the two samples would be independent. So in this way, you then realize that here we consider some data pooling. Yeah, attention is placed. Yeah, yeah, we pooling data. So when we pooling data, you have what? You have x1 bar minus x2 bar would be a normal distribution. Yeah, this one based on some learners mathematically. Yeah, just like for example, x1, x2, right? Or here you use what? 1 over n, 1 over n. Am I right? This is not right. Okay, cannot write in this way. Yeah, this is not right. I think at least I should do something like use x and x. But then that means what? Then that means here, this one lots only 1 over m, but I have to write here. You see? That means what? That means you have, right? And totally 2m by 1. Yeah, this is a dimension. Yeah. So I think today we just stop here. You take a break, and then yeah, soon we will have our tutorial.